Okay, so welcome everybody. Thank you very much for joining us for our weekly astrophysics seminar. And it is a distinct pleasure to host today Dr. Kristen Dage. Kristen completed her undergraduate degree at the University of Michigan in the United States and her PhD at Michigan State. And since last year, she has moved to Canada at the McGill Space Institute, where she's a postdoctoral fellow. We want to thank her very, very much for agreeing to give this talk today, especially since it is an ungodly hour where she is right now. And we feel really bad that because of the coronavirus, we cannot host her in person here where the weather is much better than Canada. And we promise that we will make it up to you as soon as conditions allow. So Kristen is going to talk to us today about ultraluminous X-ray sources in extragalactic globular clusters. And without any further ado, the floor is yours.
Thank you so much.
What we care about for extragalactic sources in our X-ray binaries is that we have our black hole or a neutron star that's accreting from a donor star, and it's creating this accretion disk because the accretion disk is going to emit an X-rays that we can actually study. So I feel bad saying this, but I don't care about most of the other physics going on in this system. And so specifically, one of the things we care about is the Eddington limit. Which is this idea that the maximum X-ray luminosity or radiation pressure is balanced by the accretor mass or the gravity. And so this value is 10 to the 39 ergs per seconds for a 10 solar mass black hole. And the question we specifically care about is what happens when our X-ray luminosity exceeds these limits? Somebody I know explained it a little bit more like a speed limit. So it's not a hard and fast rule. It's just that most objects don't get this bright, but some objects do exceed it and go brighter. So there's kind of two scenarios that could explain why these sources get so bright. One of them is that the compact object mass of the black hole or neutron, well, the black hole mass is much greater than 10 solar masses. And then we're kind of in the same physics regime that we know and love for the fainter sources. Or we have a compact object, so a black hole or a neutron star that is a lower mass object, and it's accreting in some unknown physics regime. So what's really interesting is that we have found a number of sources that are 10 to the 39 or above, going all the way up to 10 to the 42 ergs per seconds. Most of these have been identified and studied in the young star forming regions of galaxies. So this picture kind of shows you an example. I think this is M82X2, or maybe it's M51, I'm not sure. But you can see it's right, smack dab in the middle of the star forming region, but it's not the AGN or of the galaxy. Now, they're thought to have a high accretion rate that's fed off of a massive donor star, because when you're in these young star forming regions of galaxies, there's a lot of high mass donor stars available to accrete from. And there's also mounting evidence for the compact object to be a neutron star. So the first ever one was identified in 2014. They found pulsations. And so whenever you find pulsations, that means that you can't be looking at a black hole because you need a surface. And so therefore it's a neutron star. And this is kind of crazy because it means that these ULXs that are powered by neutron stars are accreting hundreds of times above their Eddington limit. So there's a few different scenarios to explain this, and one of them is the idea of maybe geometric beaming, but not everybody agrees with that. And geometric beaming is kind of saying that, oh, well, the physics isn't really different. It's just that you're only seeing, a portion of, like, it's like a flashlight pointed at you rather than isotropic radiation. But another explanation is saying, like, yes, this is isotropic radiation. It really is this bright. There's high magnetic fields that are assisting the boost in luminosity, I guess. But I'm not going to talk about those. I'm going to talk about the ones in globular clusters, which are very exciting. And we've actually, as of a couple weeks ago, we've bumped the number up to 20 of them. So I really like globular clusters. The ones that I care about that are extragalactic do not look this pretty. They're unresolved point sources, but I wanted to show you this just to remind you of like what a crazy and dynamic place a globular cluster is, because this is tens of thousands of stars all packed in together. And I like to, because of coronavirus, I have this great analogy now, which is that globular clusters are not socially distanced places. So they're, very crowded and there's a lot going on there. And for some reason, they also host X-ray binaries. So that means we get this exciting picture where we have our compact object accreting off of a star, and it's got its nice little accretion disk, but then it's also surrounded by all of these tens of thousands of stars that are all moving and gravitationally interacting with each other. So it's a weird place. These sources are really rare. Like I said, we've only just found 20 of them, but it's definitely worth the trouble because it can tell us a lot of interesting things, specifically about the question of black holes and globular clusters. So we do think that these ULXs are likely powered by black holes rather than neutron stars, because the conditions to form a neutron star ULX are not met in the globular cluster system for a lot of reasons. I have a visual to explain it. So this kind of just shows the difference between these two systems. So the ULXs that are in star-forming regions of galaxies, they're likely binary objects that have evolved together over the course of their lifetime. So I have these pictures. These are my baby chickens. So these two chickens are like inseparable and they're best friends, but they hatch together and they've spent their whole lives together, just like the ULXs in star-forming regions. These ones are also associated with younger systems. So that means that they have high mass donor stars available to accrete from. And then we also think that these systems can have high magnetic fields. Now, the ULXs and globular clusters have a very different formation history because, again, if you think back to our crowded globular cluster, there's this idea called dynamical evolution, where the star that you are in a binary with later in your life is not the star that you were born with. And so there's this idea called preferential mass exchange, where if you have two objects in a binary and they interact with a more massive star, they'll actually exchange the less massive star in the binary for the more massive one. So there's just like weird formation paths going on here. They're also associated with older systems. So because we have older systems, that means that we only have low mass donor stars to accrete from. And then lastly, there's not really any evidence for very high magnetic fields in a globular cluster. So there's just a lot of differences. So again, one of the things that's a big open question here is, are there black holes in globular clusters? So starting in the 1970s, everybody said you should absolutely form black holes in a globular cluster, but because of the gravitational interactions, they will get kicked out of the cluster as soon as they're formed. Now, newer simulations and observations are showing this may not be the case, but it's still a big open question. And with LIGO, it's actually becoming more and more important because a lot of work is pointing to globular clusters as the place where the LIGO black hole binaries that they detected merging are formed. But the problem is, from an observational standpoint, to kind of get at these questions, you need to find black holes in globular clusters first. So what do we know about black holes in globular clusters? Not that much, as it turns out. There was no observational evidence for any black holes in a globular cluster until 2007. As of now, I believe there's about 5 black hole candidates in galactic globular clusters. I don't think 5 is the right number. I think it's more like 7 or 8. There's really cool work done by the MUSE team out of Germany. And they actually used MUSE to dynamically measure 2 different black hole masses in the globular cluster NGC 3201. So we know of about 10 total black holes in globular clusters for our galaxy. But when you want to look at other galaxies, it gets trickier because the methods that you use to find these black holes in galactic globular clusters don't translate well outside of our galaxy. So that's why it's nice to use ULXs to search for black holes in globular clusters. And especially when you go really far outside of our galaxy, you know, I'm talking 16 to 20 megaparsecs away, you can really only study the brightest sources. And so what we do, it's pretty simple. So we take the X-ray positions of the ULX sources and we match them to Hubble images such as this one, and we can match any X-ray coordinates to the optical coordinates of known globular clusters. So this just highlights a few X-rays that we've matched to globular clusters for this specific galaxy. And then we can follow up on any of the ones that are very bright. So as I mentioned, we've now found 20 of these sources, but this is out of probably maybe 7 or 8 galaxies that we've looked at tens of thousands of globular clusters in their system. And because we're also using optical to identify these sources, we can study them in both optical and X-ray, which is pretty neat. So one of the ways we study clusters in optical is with optical spectroscopy. This is not the best figure, and I'm sorry, but I hope that it kind of just shows you that, and this is an optical spectrum, I believe, from Gemini. And so you're just looking at the wavelength here and then the intensity. And so what you're looking at is the stars, the light from tens of thousands of stars added together, like this picture. Imagine this picture here, but as a point source. And so there's like a lot of, this is called the globular cluster continuum. And so this is pretty typical for a globular cluster. And you can use it to, like, for instance, measure the age of the host cluster. But some of them, the host ULXs, have forbidden optical emission lines. So this is really exciting when we can find this, because this can tell us a little bit more about the properties of the donor star that our ULX is accreting from. So what you're looking at here is this backdrop is the globular cluster continuum, but above that we have emission lines from not only O3, which is doubly ionized oxygen, but also N2. So both of these are forbidden optical emission lines. And there's a source called RZ2109 that we've also studied in optical, and it has these amazing forbidden emission lines that we've been monitoring over the last 10 years or so, and we've seen some pretty cool things. So these are mostly spectra that we've taken with SOAR and some Gemini spectra. And what you're looking at here again, so we have the wavelength on this axis, the flux over here, and this is our globular cluster continuum. But rising above the globular cluster continuum is this emission line complex. So this is also doubly ionized oxygen emission O3. Now O3 typically has very narrow lines, but for some reason we have these regions here, this blue shifted wing and this red shifted wing. And this is probably the only source we know of that has broad O3 emission rather than narrow. And as you can see, it's the amount of flux in each of these components has changed over time. And we can use this and we can make measurements and we can see that it's evolved over time. So you can see that the amount of oxygen being emitted was in a long-term decline, but for some reason, about a few years ago, it actually got brighter. So that's something strange, and we're not sure why it's behaving like this, but we can use it, like I said, we can use it to tell things about the donor star of the system. And in this case, we know that we have a lot of oxygen being ionized in the system. Previous work has also looked for evidence of an excess of hydrogen and found none. And so that means that we think that the donor star in the situation is a carbon-oxygen white dwarf, because that's kind of the only object that when it's being disrupted can give you a lot of oxygen but no hydrogen. So that's one of the first evidences for a low mass donor star being created in a ULX system. I always forget about this slide. Okay, so what about these other sources I mentioned? So I just wanted to show you, these are X-ray images. So these are this is probably the first ones besides RZ2109 that we followed up on. This one is the Galaxy NGC 4472. So there is another ULX that's not pictured because it's very, very far out of the picture. It would not be on my computer screen. And then this source is the Galaxy NGC 1399, and it had a third ULX that was bright in X-ray for maybe about 10 years. And then in 2003, it just turned off and it wasn't bright anymore. So that one is also, like, I find that a very fascinating source because, you know, we have these ULXs that are persistently bright for over 20 years. And then we have another one that just decided to turn off. So here's some new ones. This is pretty new work for ULXs in M87. So M87 has a huge system of globular clusters. So it makes sense that we're finding a lot more ULXs in them. And then this is our 3 new friends that we found, which is exciting. And this one I found really interesting because they're all a lot closer to the galaxy center, as are the ones in M87. So just going back here really quickly, you can see that most of the ones in M87 are also around the galaxy center, but this source that we found over here was in the Virgo cold front. So that was really, really far from the galaxy center. So that means that of the 20 ULXs that we found, about 3 of them are just really far away from the galaxy center, which is odd. And so one of the things we can do with the X-rays is we can look at X-ray variability. So these are all light curves. So this just shows the count rate in the object over the course of the observation. So this is typically a way we can search for variability on the scale of hours. And I find it really interesting. So this source actually dropped by about a magnitude of 7, like a factor of 7 over a course of about 5 hours. This is the light curve of the source that turned off. So it seems to have been highly variable before it turned off. But this one we're still observing to this day. And it does also show these flares in brightness in some other observations. This source, I'm not sure what to make of it because it seems like it was pretty variable in maybe a couple of observations, but it's mostly steady. For the most part, all of the other ULXs that we have good enough data to extract light curve from do not show temporal variability on a short term, which is odd. So yeah, like I said, this is most of them. I haven't updated it for the new sample yet, but I don't think that they'll be super variable either. Now long-term, this figure didn't turn out great either. So this is just showing some of the sources, the total X-ray luminosity for the observation over the entire data set that we have. So this data set spans about 10 years and they don't really seem to vary too much long-term as opposed to this source. This is also RZ2109. It's just a really fascinating source. So this is a 16-year data set, and you can see that the X-ray luminosity jumps all over the place. My favorite data points are these. So these 2 observations were taken a week apart, and yet it jumped by a huge amount in brightness. So I would say that about roughly half of our sample varies on a time scale of months to years, but the way they vary is not always the same. So one of the other things we can use X-ray studies of these sources to ask is the question of, do they show changes in spectral variability that correspond to changes in X-ray luminosity? And so one of the things I'll use as a proxy for that is the shape of the X-ray spectrum. So this figure right here shows a couple of sources. These are in the same galaxy, they show up in all of the same data set, and you can see that the shape of the X-ray spectrum is a bit different for each. So this one right here, we would call it a softer. So this one is better fit by like a disk model. So it probably, like, most of the emission is coming from a disk. Whereas this source right here, see how it has a lot more higher energy photons. So there's some other mechanism that's producing this higher energy emissions. So it's modeled a bit differently. And so what we want, the question we can ask here is, does the shape of the spectrum, or like what's producing the X-ray emission, does it change as the sources get brighter or fainter? And so for the sources that are better fit by that power law model, so that's the one that produces the harder emission here, we can just fit it with the power law. This is kind of how we can answer the question. So this axis shows the X-ray luminosity, and then this shows the best fit spectral index for all of these sources. And you can think of this as a proxy for the shape of the spectrum. And I honestly have no idea what's going on here. So it's kind of weird. Because the model that we used has no physical interpretation, it's really unclear how to interpret this. But when we look at the sources that are best fit by an accretion disk, it kind of makes a lot more sense. So again, we have X-ray luminosity on this axis. And then on this axis, we have the accretion disk temperature, which is the kind of the best fit parameter for the shape of this model. And one of the things you notice is that for this source right here, you can see that there's a clear correlation. As the X-ray luminosity goes up, so does the temperature. And this is a relationship that seems to correlate with something we know and love, which is the Stefan-Boltzmann law. So the luminosity goes about like T to the 4. So a lot of galactic black holes follow this trend as well. This is something we understand. But these sources over here are kind of odd, right? So you can see, especially in this purple one, that the temperature is essentially the same over a huge range of X-ray luminosities. And that's just kind of weird. And the other thing you'll notice is that the value of the temperature is very distinct for these. So for this source, that kind of the sources that behave like this have a higher disk temperature, and whereas these sources have a lower disk temperature. Now, another question we can ask here is the optical emission I was talking about earlier. Can we tie all of this together? And so we happen to have spectra for a few of these sources. So for this one, this is its optical spectrum. And this is just the regular old globular cluster continuum here. There's nothing much going on. Anything that looks kind of interesting is probably due to like skylines or bad subtraction. So, you know, that's too bad. But remember that we have these other two spectra here that have optical emission. And as it turns out, both of these lower temperature sources that have this strange non-relationship between X-ray luminosity and disk temperature are also the ones that host optical emission lines. So what does this mean? So potentially, and like we don't really have the sample to say this yet because it's just so hard to find these things, but it could be that the sources that behave like this, they have higher disk temperatures and do not have optical emission, are the scenario, the first scenario that we talked about all the way back in the beginning of the talk, where we have slightly more massive black holes that are accreting in normal physics. So I call them boring. I know that's not very nice of me, but the other scenario is just so much more exciting because this optical emission is potentially linked to outflows. So that means that we could have less massive stellar mass black holes that are accreting in some unknown regime of physics. And that's just super cool. The other thing I wanted to touch on very briefly is the optical properties of the host clusters. So one of the questions we can ask now that we have a little bit more of a larger sample size is, how does the properties of the host cluster link to whether or not it hosts a ULX? So this figure here, this is called the color magnitude diagram. And what it's showing is the absolute magnitude in one band of all of the globular clusters. And then this color is, you just take two different filters and subtract them. And then if they'll tell you if they're redder and more metal rich or bluer and less metal rich. And one of the things that's kind of interesting here is you can see that most of the globular clusters fall into the globular clusters that host ULXs are correlated with being brighter clusters, and this makes sense. This is a property that we know for a lot of X-ray binaries and globular clusters, because brighter clusters are larger and have a bigger population. So I think there's just more of a higher probability to form these sources. But one thing I find interesting is that we don't have a significant larger number of redder globular clusters than bluer globular clusters. So some people that do studies of low mass X-ray binary populations in globular clusters have shown that there's a correlation between a redder cluster and hosting an X-ray binary by 3 to 1. And we don't probably have the numbers yet, but that's not something we see quite yet, which I find interesting. But to me, the main takeaway of this plot is that the kinds of clusters that host ULXs are not your typical cluster. And so you can see that the contour plots show the population of like all of the globular clusters that don't host ULXs, and they're two pretty distinct populations. So just as kind of a summary, what are some physical implications that we can take away from this? So we now have 20 globular cluster ULXs, and it seems like their X-ray behavior falls into a few distinct categories. And to me, the distinct categories in X-rays imply that they have different accretion physics, and therefore they probably form differently from each other. So I think it's really interesting that even with only 20 clusters, we have evidence for like a diversity in how these sources were formed. And then also we have this one source that is likely feeding off of a white dwarf. I think that's really fascinating because, you know, who knows that disrupting a little white dwarf can allow you to have really high X-ray luminosities. Optical spectroscopy is a really useful tool for this, and it can reveal something just bizarre and hidden about these accretion physics of these sources. And then even though the brighter clusters tend to host ULXs, we don't see an overabundance of metal-rich hosts, which is also really interesting. And it'll be interesting to see as we find more of these sources, will this hold up? So as a summary, I hope I've convinced you that globular clusters are a really exciting and dynamic place to be. And I think studies of X-ray binary formation within the clusters are going to be really, really interesting going forward, because we don't know, like, are these X-ray binaries that have formed through dynamics, or is there a possibility that an external source is interacting and disrupting the binaries, such as the Kozai mechanism? And the other thing is that as we find more sources, it's becoming more and more clear, like what we can call like the typical behavior of the sources versus the abnormal sources. So we found a lot more sources. I didn't show them all because it made the plot look messy, but we have a lot more sources that follow this relationship and have higher disk temperatures, whereas we still have only found 2 of the sources with the very low temperatures. So I think there's a lot more things out there to discover. That'll be exciting.
Thank you very much, Kristen. And do we have any questions? I already see one raised hand by Konstantinos.
Hello, Kristen. Thank you very much for your talk. I have 2 questions. First of all, you mentioned this possibility that the white dwarf is the donor. Mm-hmm. But I'm wondering what kind of mass transfer mechanism could actually get that much mass from a white dwarf. Have you seen these possibilities?
So this is the source that's really weird. And it has, like I said, it has this huge amount of optical emission. So it's one of the things that we found, I didn't talk about it too much because we have a little bit of conflicting measurements, but there's a 2014 paper by Mark Peacock that found evidence that there is a huge oxygen nebula within the cluster. So it would actually flood most of the globular cluster with oxygen. And so like whatever caused this to happen means that we have a huge pool of oxygen to accrete from. But I think it's, besides knowing that we have this huge nebula to accrete from, I don't know that we have like a good idea of the mass transfer mechanism yet, because it's just hard to model.
Yeah, because a white dwarf would be a very untypical donor system.
Yeah.
Well, the second question is regarding these systems that do not seem to change the temperature as the luminosity changes.
Mhm.
And I'm thinking whether that could be a sign of a beaming mechanism, especially in case you have neutron stars. Now, in the beginning, you said that neutron star ULXs are probably not allowed to be in a globular cluster system. But recently, there are studies like MISRA and TAL 2020 that show that you may have neutron star systems with donors of intermediate mass, like 2 to 8 solar masses that may possibly be in a globular cluster system. It's not your typical systems. So is there any recent study about globular clusters and what type of populations you would find at binaries? Or is this something that should be updated?
So I think there's a couple of parts. So one is you were asking about beaming for these specifically. And these, both of the ones where the LX does not change with KT, both of those are ones that have optical emission associated with them. And when you have optical emission associated with a source, you can actually use it as a way to place constraints on the amount that the source could be beamed by. And so Mark Peacock has a second 2014 paper actually placing constraints on beaming, and he ruled beaming out completely for this one source. And I do agree with you. I think that paper is pretty interesting, and I think it's something that should be updated. But I think, like, as far as like the way I see it is that most of the way you can explain a neutron star ULX getting a high accretion rate is by invoking a high magnetic field. And there doesn't seem to be any evidence for high magnetic fields within at least galactic globular clusters and studies of neutron star populations there.
I see. Thank you very much.
We have a question from Andrea Zezas.
Yeah, thank you, Kristen. That was a very, very interesting presentation, and have a lot to discuss with you. So I would like to focus on two questions right now. The first one is that you say that these are most likely white dwarfs because there is no hydrogen in their optical spectra. Now I was wondering, is there any chance that the emission lines from hydrogen are hidden within the absorption lines from the stellar component in the globular cluster?
That's a good question. So I think Matt Steele had a 2012 or 2014 paper. And so what they actually are looking for is significant hydrogen emission above the globular cluster continuum. I think the idea there is that if, if we have, this huge amount of oxygen, we should have enough hydrogen where it should, counteract the hydrogen absorption from the globular cluster continuum, like you said. And so they were actually able to place constraints on the amount of hydrogen in the system and found a very low amount.
I see. Because there is a technique that we're using a lot in extragalactic spectra where we subtract the stellar component. So we use a model for the stellar component, we subtract it, and then we get the pure emission line spectrum.
Yeah, that's what he did.
Okay, perfect.
Yeah, he did that.
Okay, perfect. And still there's not enough hydrogen.
Yeah,
Okay.
He modeled it, so he was able to measure the age as well of the cluster.
Okay, that's very interesting then. Because then the question is, if you have a white dwarf, I mean, how on earth can you have such a high accretion rate to sustain a ULX with a white dwarf?
Yeah, I think that's something, I know Tom Macaron has models that I don't think I completely understand, but I think that because we have, like, there's this idea that we have this huge pool of oxygen to draw in from. So as I think as the compact object moves around in the binary, it can also pull from the oxygen nebula in the system as well.
Okay, it's still very weird, but
It's still very weird. I'm not going to pretend that I understand what's going on here.
okay. Anyway, and then I have another question related to those sources being in globular clusters. So when we're looking at low mass X-ray binaries in globular clusters, there was a strong correlation between the presence or the probability for a globular cluster to host a low mass binary and what is called the gamma factor, which effectively combines the mass of the globular cluster or its absolute magnitude and its effective radius, and effectively tells us what is the interaction probability of the stars within the globular cluster. So have you looked at whether those objects, those globular clusters that tend to host ULXs, tend to have higher gamma factors, for example?
I have not. I think that's something that would be really interesting to do, though.
Okay, because it would be interesting to compare those with the globular clusters, for example, that host low luminosity X-ray binaries. Do they have like some something different in their properties or in the interaction history, which can be parameterized by this gamma factor?
That's a really, really good question. I think actually the galaxy I'm working on now, NGC 1316, would be the perfect place to do that. Because when I was going through that, so like I've only found the 3 ULXs, but there was a number of lower luminosity X-ray sources that aligned with globular clusters as well.
Okay, perfect. Yeah.
Any other questions for Kristen? Okay, if there aren't any more questions, let's thank Kristen very, very much again. Thank you for this wonderful talk, and clearly there is lots to be discussed with people here. So we will be looking forward for an opportunity to actually physically host you in Crete once the pandemic goes away. Thank you very much again, and thank you everybody for joining.
Thank you.